Professor Bumbleweed here. That nice grassy mountain looks innocent enough. Cows, sunshine, zero chaos. Cute. Underground, magma and gases push against rock, and pressure stacks up like someone cramming luggage into an already full suitcase. This stays a few minutes long, keeps the tone playful, and still delivers the real science behind eruptions. If you like calm landscapes with secret problems beneath them, you are in the right place. All right, closer look time. Magma forms when rock underground partially melts. It stays thick, heavy, and full of crystals, so no, it does not act like a clean neon liquid. The melt sneaks upward through cracks and tiny spaces, then gathers into a storage zone under the volcano. That stored magma pushes outward on the rock walls around it, and it also carries dissolved gases that hate being trapped. So the calm surface sits there looking peaceful, while the underground system does the actual work. Magma carries gases, mostly water vapor and carbon dioxide, mixed in under high pressure. Deep down, that gas stays dissolved, so everything acts calmer. As magma rises and pressure drops, gas comes out as bubbles, like opening a fizzy drink, except the bottle is rock. Bubbles take up space, so the magma expands and gets more buoyant, which makes it rise even more. That feedback loop ramps up pressure fast, especially if the pathway stays blocked. When magma collects in a chamber, it pushes on the rock walls like air in a tire, except the air is molten rock with expanding gas. Add more magma from below, or trap more bubbles near the top, and pressure rises. The surrounding rock can flex a little, so the ground might bulge subtly, but rock has limits. If the chamber keeps pressurizing, cracks start forming, and those cracks become the escape routes magma desperately wants. Volcanoes are basically geology trying to find the weakest point. Pressure has two options: stretch the rock or crack it. Rock stretches a little, but once it reaches its limit, a fracture opens. Magma takes that opening and turns it into a weapon, injecting upward as a dike and forcing the crack wider. Sometimes the intrusion stalls and cools, basically failing the mission. Sometimes it keeps climbing because pressure stays strong and the rock ahead keeps breaking. The important part, cracking rock, is how stored pressure becomes movement toward the surface. Think of a volcano as a plumbing system made of cracked rock. Magma rises as dikes, thin vertical sheets, because pressure forces the rock apart. Sometimes it spreads sideways as sills because certain layers are weaker and easier to pry open. Over time, repeated intrusions can create a main conduit, a rough, semi-open route that magma reuses. None of this is neat. It is pressure, rock strength, and molten material fighting for space. The surface just sits there, pretending nothing happens. Classic. Near the surface, rock breaks easier and gases expand more. That combo makes pressure changes dramatic. Gas can escape first through cracks, so the volcano starts venting like a stressed kettle. If the crack widens into a real opening, magma follows. That is the moment pressure stops being trapped underground and starts doing work above ground. The vent grows as rock crumbles, and even small spattering shows the pathway is open. After that, the style of eruption depends on magma, thickness, and gas content, which is where things get fun. Not every volcano goes boom the same way. If magma is runny, gas escapes more easily, so pressure releases in smaller bursts. That often creates lava flows and fountains, still dangerous but less like an instant cannon. If magma is thick and sticky, gas stays trapped as bubbles. Pressure climbs and the magma can shatter into ash when it finally breaks free. Same basic cause, pressure underground, different outcome because the magma's viscosity controls how easily gas escapes. So yes, magma texture decides whether the volcano behaves like a leaky hose or a shaken soda. Viscosity controls whether pressure leaks or launches. Low viscosity magma flows easily, so bubbles rise and vent, bleeding pressure off. High viscosity magma resists flow, so bubbles struggle to escape and instead build a trapped, expanding gas network. Put that under a plug, and pressure rises quickly. When the plug breaks, decompression is rapid, gas expands, and magma shreds into ash. That is why sticky magma and explosive eruptions are frequent partners. The volcano does not decide to explode. The bubble physics forces the issue, efficient, terrifying, very on-brand for Earth. Scientists cannot see pressure directly, so they watch for clues. Rising magma cracks rock, which creates small earthquakes, tiny shakes that instruments pick up. Pressure can also deform the ground, making the volcano swell by centimeters, which GPS stations and satellites detect. Gas output can change too, because gases escape through vents as the system pressurizes. None of these signs acts like a perfect countdown timer because volcanoes love to be complicated. But together, earthquakes, deformation, and gas changes reveal when pressure underground is increasing and pathways start opening. A dormant volcano can look like a postcard and still have an active system underneath. Dormant means it does not erupt recently, not that it is empty or permanently safe. Magma can still move in from deeper sources, refilling storage zones and rebuilding pressure over time. Gases can accumulate, rock can crack, and pathways can start forming again. The surface may show nothing more than a quiet hillside, but underground, the pressure setup can restart. So the cows keep chewing, and the volcano quietly reloads. Nature is polite like that, until it is not. Back to the calm volcano scene, because the whole point is what you don't see underneath. If this breakdown helps and keeps you awake, hit like. It's the quickest signal that this kind of science explanation is worth making more of. Instead of guessing and being wrong in public, appreciate you watching. The cows remain unimpressed, but I try anyway. If there's a science topic you want next, leave it in the comments. Pick something concrete: earthquakes, tsunamis, black holes, volcano monitoring, whatever. It keeps the series pointed in the right direction, instead of me guessing and confidently teaching the wrong thing. Thanks for hanging out with Professor Bumbleweed. See you next time. Same silence, better knowledge.